listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. The topic of coaxial connectors has really been gaining popularity recently because of its reliable quality and the ability to support greater cable lengths. But there are a lot of rules to follow when using coaxial cables and their cable assemblies. In this podcast, we'll discuss the function of coaxial cable and give an overview of operation. We'll also discuss environmental factors, managing a customized cable assembly, and then identify cable attenuation. First, we'll start with the basics, the function of a coaxial cable. This is to deliver an RF signal from point A to point B through various connector interfaces. Worth Electronic offers a wide range of quality cable assemblies, and this article is based on Worth Electronic's standard cable types. It also helps to understand which points to consider when selecting a cable for custom-tailored cable assemblies. Coaxial cable is a different type of transmission line. It's used to carry high-frequency electrical signals with low losses. It's different from electrical wire and other shielded cables because the dimensions of the cable and the connectors are controlled to give a precise constant conductor spacing, and this is needed for it to function efficiently as a transmission line. Coaxial cable conducts the electrical signal using a center conductor surrounded with a dielectric layer and then enclosed by shielding. This is typically 1 to 4 layers of woven metallic braid or tape. Most coaxial cables are protected by an outer, non-conducting jacket. Different standard materials used for each of these parts include a solder or a standard Cu center conductor, PTFE or FEP dielectric, a single or a double layered shielding or braid, and a jacket typically made of PVC, PE, or FEP. Our next goal is to help the user determine the appropriate coaxial cable type for an application according to each cable's characteristics. Now, to reach this goal, we'll take a look at the attached Table 1, and that gives an overview of common cables and their properties. Using this table, we can walk through coaxial cable selection step by step. The coaxial cable portfolio from Worth Electronic covers 2 main cable types. This includes the 50-ohm flexible cable as well as the 50-ohm hand-formable cable. Most coaxial cables are identified by an RG or radio guide number. This is a designation given by a military specification. Cables vary by size, conductor, dielectric, shielding, and jacket materials. The different RG numbers for each type of coax cable are helpful to distinguish their unique characteristics and specifications, though the numbers themselves don't generally have any specific meaning. Underwriters Laboratory, commonly known as UL, assigns a different style number for each approved appliance wiring material, AWM construction. It also lists a few specifications, such as gauge size range, insulation material, temperature rating, and voltage rating. Users can access information about AWM wires on the UL website. If you're looking to find the appropriate coaxial cable for a given application, then you need to look at the 6 main selection criteria, such as impedance, frequency of operation, cable attenuation, temperature range and environment, bending radius or flexibility, and the thickness. First, the check impedance. The 2 main cable impedances on the market are 50 ohms and 75 ohms. Worth Electronic cable assembly products are in the 50 ohms. The application and device will determine cable impedance required. Next, the frequency of operation. Now, it's important to consider the signal frequency as each cable has different performance parameters. Higher frequency signals suffer from greater resistive loss due to skin effect and this can result in greater attenuation. Cables are also limited to a cutoff frequency due to their physical size in relation to the signal wavelength. Take a Wi-Fi application, for example. Now, if the system only requires a 2.4 gigahertz channel, an RG178 cable could support it. If the system is running both 2.4 gigahertz and 5.8 gigahertz bands, it must use a higher rated cable from the DC around 6 gigahertz category. Then we'll move on to cable attenuation. Cable attenuation represents the amount of signal loss over a specific distance, and this is given in units of decibels per meter. A more expensive, low-loss cable may prove to be a more economical solution than a cable with higher attenuation that requires an additional signal booster. For example, if you wish to use the FM frequency of 108 megahertz, there is RG58 and RG174 to select from. Comparing the attenuation at 1 gigahertz, RG58 is 0.56 decibels per meter, and RG174 is 1.09 decibels per meter. Now, ideally, RG58 would be a good choice if only taking attenuation into consideration. However, we need to consider other characteristics, such as cable bending radius, cable thickness, etc., etc. When we discuss temperature range and environment, we need to take protection into account. Cables may be used in different environments, depending on the material used. Most cables with PE or PVC jackets can be used up to 80 degrees Celsius, and cables with FEP jacket range up to 200 degrees Celsius. This jacket also provides environmental protection. PVC is a robust and durable material. It's widely used on economical cables. PE is advantageous against moisture, weather, and UV resistance. It's really ideal for outdoor applications. And then there is FEP, and this has additional protection against oil and chemicals. In our attached figure 2 of this podcast, you'll see the cable temperature range graph to help you select the required jacket. A good example of this is a telecommunications system that requires a lighter weight and operates at higher frequency points, like 0.085, 0.047, and 0.141 cables would be a good product choice. Hand-formable cable with its outer conductor of tinned braid is often preferred for easy installation, where it can be protected inside of a device. Flexible 0.047 and 0.085 equipped with an FEP cable jacket provides advanced protection against oil and chemicals. Specifications define these cables can reach up to over 200 degrees Celsius. From a product assembly point, above 165 degrees Celsius is more appropriate when it comes to soldering process. Now, when we talk about the bend radius or the flexibility of a cable, this represents the sharpest bend the cable can withstand without potential damage and degradation of performance. Overbending the cable damages its internal structure, and it will directly result in poor electrical performance of an assembly. Cable bending radius does not have a direct result to cable thickness. There are a few influences according to cable structure, like center conductor structure and whether it's a solid or stranded, the layers of shielding or braid, and also the material of the cable jacket, and finally, the thickness of the cable. Knowing the cable's outer diameter is often helpful for cable installation. Worth Electronic offers a made-to-order cable assembly service, which reduces the user's assembly workload and manages the requirement of reliable signal transmission. So here's what to consider and what's required information to get a cable assembly. First, connector 1 and 2. Check the interface, orientation, or ingress protection function. Second, heat shrink tubes. Check specific length, color, or customizable text. Third is the label. Apply the standard Worth Electronic part number or customize the content or add a special label. And last, check the definition of length. The strip end could make assembly easier for the user according to these types of strip. First is the stripping dimension, and here usually the tolerance is specified. In the direct cut, the user strips or performs assembly using another method. The tinned braid or the pigtail strip assembly allows users to quickly make the cable perform without a connector or even proper shielding. The tinned braid avoids splay or damage during transportation, and it's easier for assembly. And finally, there's the tinned center conductor. The tinned stranded center conductor is helpful to prevent damage during transportation. It also makes it easier for assembly. But an open, exposed end of the assembly should be taken into consideration to avoid the risk of crimping or vibration applications. In order to identify coaxial cable attenuation and other characteristics, we first need to know the characteristics and select the cable type. So a quick method to selecting a cable type is through its nominal working frequency range. At Worth Electronic, there are 4 ranges of frequency for standard coaxial cable types, including DC up to 1 GHz, 3 GHz, 6 GHz, and 18 GHz. For example, when selecting a cable assembly for FM radio, the working frequency is mainly about 800 to 900 MHz, and the option could be RG58, RG174, or even RG178. If you only select the cable by attenuation specifics, then the ideal choice is, of course, the RG58, because it presents the best attenuation result. However, we need to consider the other characteristics, such as cable thickness, flexibility, and the weight. RG178 could be the ideal option based on its covering the frequency range up to 3 GHz. However, its higher attenuation performance is related to its thickness, and the advantage of its weight and the FEP cable jacket. On the Worth Electronic datasheet, we provide typical cable attenuation graphs to let the user easily calculate attenuation at different cable lengths. This helps you quickly determine how a specific frequency point would perform when a cable length changes, to match the cable routing need to other factors. So if you need to know how 5.8 GHz attenuation changes between 3 feet and 5 feet lengths, then using an assembly of SMA straight plug to SMA straight plug on RG316 double braid cable, here's the attenuation table and the formula as shown in Figure 7 of this podcast. Now the formula is the attenuation at the desired cable length equals the length per 100 feet divided by the factor in feet for normalization to 1 foot times the desired length multiplied by feet. So using this formula to calculate attenuation of 3 feet at 5.8 gigahertz would give us 2.46 decibels. The calculation of attenuation of 5 feet at 5.8 gigahertz gives us 4.1 decibels. The attenuation of 5.8 gigahertz of 2 extra feet is 1.64 decibels. The attenuation difference gets larger because of the higher working frequency point and the length of cable. In summary, coaxial cables are widely used as transmission lines for radio frequency signals. The quality of a coaxial cable assembly is related to many production and assembly details of the product. However, remembering all of these details of coaxial cable types can be very complicated. After listening to these suggestions, we hope you now understand what critical points to check when selecting coaxial cable. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.